Okay, so I'm going to share my screen now. Okay, I hope you are able to see the screen. Yes?
Yes, sir.
Okay, good. Thank you. Okay, so before I begin today, well, today's lecture is going to be on, okay, so yesterday we covered uh, the algorithmic part of data compression and source coding, right? We looked at the two main algorithms, which are Huffman coding and uh, yes. I think somebody posted a comment about uploading the videos. So yeah, I will do it today. Okay. Yeah. Okay. So uh, in terms of the algorithmic aspect of the data compression and the source coding that we are going to study, that was the content of yesterday's lecture, right? We looked at Huffman coding and Lempel-Zhu coding. By the way, I mentioned this yesterday after some of you left the lecture session, that one of the textbooks of this course that we have mentioned earlier is a book by John Proekes. The name of the book is Digital Communications. So you should read chapter 3 of that textbook. Actually, even chapter 2, because chapter 2 is covering a lot of the probability theory topics that we have studied earlier. And then chapter 3 is on source coding. So that chapter is actually, it has a nice description of the crafts inequality that we studied yesterday, as well as the Lempel-Zhu coding and the Huffman coding. Okay, so I strongly suggest that you go and read that chapter. You may be able to find bits and pieces of all the different topics of source coding online or maybe in some other book. But this chapter 3 of John Proekes' book is like one-stop shop, right? You will get everything over there. Overall, I think I recommend Proekes' book. It's a very nice book on the topic of digital communications. Okay, so now in contrast to yesterday's lecture, today's lecture, which will be the last lecture on the topic of source coding, from next week we will move on to channel coding, the next block of our communication system. So today's topic is going to be more of a conceptual aspect. Okay, and I hope that it's not going to be too much of a stretch for you. In fact, it's something that you know already, but we'll be taking a kind of a different look, different viewpoint on something that is little kind of obvious. Okay, so that is going to be the topic of today. So before I begin, let me ask you this question. So, you know, the coin that we toss, or let's say the captain of a cricket team tosses in the playground, heads means the toss is won by the captain, tail means the other person wins. So tossing a coin is something that we know all very well, and we have said that it can be modeled as a binary random variable. Specifically, we have called it the Bernoulli random variable, right? And let us say that this Bernoulli random variable has a probability of turning up 1. Maybe 1 is assigned to heads, 0 is assigned to tails. So let us say that we call heads as 1, and let's say that this coin is a little bit strange. Typically, we would expect 1 and 0 to occur with equal probability, but here we are assuming that probability of 1 is equal to P, right? So that is our notation. Sometimes we have called it to be Q, but here I'm going back to calling it P. So this is the probability of Bernoulli random variable turning out to be 1. Okay, so my question to you is that suppose okay, so suppose I perform this tossing of the coin. Suppose I toss the coin 10 times, and let us say that this coin, for this coin, the way it is manufactured, P is equal to 0.3. So it's like 70% of the time, the coin lands up on tail, and only 30% of the time, the coin ends up landing on heads. So P is equal to 0.3. And let us say that I perform the experiment, or more informally, I just toss the coin 10 times. Then what do you think? How many heads will I see and how many tails will I see out of 10 tosses?
3 heads and 7 tails.
Sorry, can you repeat?
Heads and 7 tails.
3 heads and 7 tails. Now, is that the case? I mean,
But sir, it depends. As 10 times we are tossing, so head can be 0, 1 time, 2 times, 3 times, increasing till 10.
yeah, so Somin gave the right answer. You know, we are tossing the coin 10 times, although the value of P is 0.3, that doesn't mean that always, every time we toss the coin 10 times, we are always going to get 3 heads and 7 tails, right? Put it other way. Let's say P is equal to 0.5. Let's say it's the regular coin. And if you toss it 10 times, do you think every time we are going to get exactly 5 heads and 5 tails?
No.
No, sir.
No, sir.
I mean, this should be pretty clear, right? I mean, forget about tossing a coin. Birth of a child is also a Bernoulli random variable with P equal to 0.5. So we see a lot of families where maybe there are 4 children that the parents have, and although P is equal to 0.5, it is not that every time 2 of them are boys and 2 of them are girls. Sometimes all 4 of them are girls. Sometimes all 4 are boys. Sometimes there are 3 girls, 1 boy. Sometimes there are 1 boy, 3 girls. I mean, sorry, 3 boys, 1 girls, and so on. So there is all possible outcomes, starting from 0 boys, 4 girls, 1 boy and 3 girls. 2 boys and 2 girls is also possible, definitely, because P is equal to 0.5 in this case. But you can also get 3 boys and 1 girls, and you can get 4 boys and 0 girls. Okay, now let me go back to this tossing of the coin part, and let's go back to P being equal to 0.3. So, yeah, so like somebody said, if I toss the coin 10 times, I don't know. the number of heads out of 10 would be 0. I might get all 10 tosses to land up tails, or I might get only 1 head and 9 tails. Or it could be the other way. I might get all 10 to be heads and 0 tails. But now let me say that instead of tossing it 10 times and looking at how many heads I got, suppose I toss the coin 10,000 times. Then what do you think is likely to happen?
Sir, head or tail will come around 5,000 times. It's
So
most
P is
probable.
equal to 0.3, remember?
Oh, so sir, 3,000 times, around 3,000 times.
Yeah. So Vandan, I think, is giving the right answer. That if n is small, then I can't be sure. I might get all of the n experiments to turn out 0, or I might get all of them to be turning out 1, or it could be any values in between. That is when n is small. But if I keep on increasing n, then I am more and more going to be certain that I will see exactly, let me call the number of times that I see 1, let me call it as n1. Sorry, this is so n1 is equal to one here. Okay, n1 is, I'm going to call it as a number of ones that I observe in an experimental trials of Bernoulli random variable with probability of P. Then what I say is that its value can be any number from 0 to n, capital N. Actually, I should call it like this. This is the set. However, as n tends to infinity, meaning that I make n bigger and bigger, then in that case, I expect that n1, the number of times that I get 1, tends to what?
P times n.
Exactly. This is going to converge to P times n. Who can tell me why?
Sir, if n is small, uh, then small change can vary the ratio n1 by n drastically. But when n increases, means n tends to infinity, then the ratio converges to some particular value.
Yes. But there is another very simple answer that I was looking for. How have we I mean, in your exam, the first question was, what are the three ways that we define probability? And then
Asymptotic.
there was one answer to that question, which here you can right away give to say why this has to be the case.
That relative frequency.
Yes.
Experiment on that.
Pujan is giving the right answer. What is the relative frequency definition of this probability P?
N1 by n, as limit n tends to infinity will give probability.
So, exactly. So Pujan has said that, and so I will write it here. Because a little bit. Because this is how the probability P is defined. Meaning that P is equal to limit of n tends to infinity and 1 divided by n. And so as you keep on increasing n, and if n1 ends up being some value other than P times n, then the probability is not P, it is that some other value. Right? So if you're saying that the probability that the coin will end up on the heads is equal to P, then you better observe the number of ones converge to P times n as n becomes large. Okay, so this is the part which I was telling you that you all kind of know this. I mean, it's kind of obvious. And so the rest of today's lecture is going to we will be looking at this in a little different manner, which is actually quite interesting. It kind of will hopefully make you think about the way the information is structured. Okay, so, but in order to be able to do this, let us kind of go over this binomial distribution. And I mean, ultimately we are going to, at the end of binomial distribution study, we are going to kind of conclude the same thing that I have written here in the black handwritten form, right? This is what we are going to say at the end. But we are going to make that in a mathematical manner using binomial PDF or PMF. Okay, so let us come back to this question that I'm performing this experiment 10 times and Bernoulli variable has a probability of P turning up 1. And so if I do this experiment, let's say 2 times, 3 times, 4 times, what happens? And I want to also look at what is the sum of all this n binary outputs. Because it is the sum that we have defined as binomial random variable. This is what you have studied in one of your earlier labs. Okay, so if I do the experiment 2 times, and by the way, there is this typographical mistake here, spelling mistake, so please pardon me. So if I do the experiment 2 times, then these are all the 4 possibilities. Maybe I get 2 zeros, I get 0 and 1, I get 1 and 0, or I get 2 ones. And so if I add up the values that I get, then these are the answers: 0, 1, 1, and 2. If I do this experiment 3 times, then these are the 8 possibilities. And the summation is what is listed here. For these 2 cases, I get 1. This one here, I get 2. And then again, I get 2 when the 3 experiments turn out to be 101 and 110. I get 0 only 1 time when all of them are zeros, and I get 3 only 1 times when all of them are ones. So that is the pattern that I see. I get y equal to 0 only 1 time when all 4 experiments, when n is equal to 4, are 0. And I get y equal to 4 also only 1 time when all 4 of them are ones. And then there are many different ways that I can get ones. There are many different ways that I can get twos. And there are again several ways that I can get threes. Now, you may have studied from your earlier math courses that the total number of ways that you can get, let's say, y equal to 1, is given by this binomial coefficient. It's called n choose y. So when y is equal to 0, n choose 0 is always equal to 1. That is how this binomial coefficient is defined. And similarly, when y is equal to n, again, n choose n is always 1. And so that is why it doesn't matter if n is equal to 4, 3, or 2. The number of ways that I can get 0 or the number of ways I can get y equal to n is always going to be 1. It's always going to be the first row and the last row. But then if I want to know how many ways I can get y equal to 1, then I go back and look at this table. Here, I will get y equal to 1 only 4 times. 2 here, 3 here, and 4th time here. And the reason for that is that n choose 1 is always equal to n. Similarly, n choose n minus 1 is also equal to n. And so therefore here I will get 3 also 4 ways. You'll see that. I'll get 3 1 time here, 1 time here, and then 2 more times here. Now, this way I can answer any question of how many ways I will get y. I'll get y equal to 2 n times n minus 1 divided by 2 times, and so on. Basically, I just look up the binomial coefficient, and that is the total number of strings here. When n is equal to 4, n choose 2. 4 choose 2 is equal to how much?
6.
6. And so that's why we get the value of 2 6 times. 1, 2, 3, 4, 5, and 6. Right? Now, the other thing that you will notice, and this I want you to keep in mind because I'm going to ask you a question later on. So this time I'm telling you the answer, but next time It's going to be similar question, but I won't tell you the answer. We are assuming, so assume that the source, the Bernoulli source, is DMS. Well, D part is obvious because it's Bernoulli, it's binary, it's discrete. But the main thing that I wanted to highlight is that we are assuming that it's a memoryless source. Because it is memoryless, all the N experiments are going to be independent of each other. And because they are independent, it doesn't matter which one of this N choose Y string I pick. All of the strings will have the same probability, which is given as P raised to Y times 1 minus P raised to N minus Y. Why is that? Because if I go back to this table, and if I want to see what is going to be the probability of me observing 0, 0, 1, 1. Well, first 0, that probability is 1 minus P. Second 0, that probability is going to be 1 minus P again. And then the next 2s are 1s. So this is going to be P times P. But this is same as 1 minus P squared, P squared, which is same as 1 minus P raised to the power 4 minus 2 times P to the power 2, which is same as 1 minus P N minus Y times P to the power 1. It may seem a little drawn out, but it's kind of again obvious. You have N minus Y zeros and Y ones. If you look at any of these 6 strings, there are going to be 2 ones and 2 zeros. And because this source is memoryless, if the symbols are independent, the location at which zeros and ones occur doesn't matter. And therefore, all of these 6 strings have the same probability, which is given as this. Okay, and so therefore now we can say that the total probability that I will observe a particular value of I is given as N choose Y, which is the total number of strings, total number of ways that I can observe Y, times the probability of each string, which is P to the power Y, 1 minus P to the power N minus Y. This is essentially the binomial formula, binomial PDF formula. Okay, so now let us consider one specific problem which is very similar to the one that I asked you at the beginning of today's lecture. Suppose we go to some factory, maybe it's a bicycle manufacturing factory, and we are told that this factory is pretty good, but still 30% of the bicycles that come out of the factory, they don't pass the quality test. So the question is that you happen to go and visit this factory and you randomly pull out some 10 cycles. What are the chances that 3 of them will fail? Now, one possible answer that you may have, actually somebody gave that answer at the beginning of the lecture, is that it's going to be 100%. Because 30% of the cycles are failing, that we have been told. I go and look at some 10 random cycles, I will always see 3 of them failing. But that won't be the right answer, as we have already discussed earlier, because 10 is not a big enough number. So actually, to answer this question, we have to use the binomial distribution. With capital N equal to 10, P equal to 0.1, sorry, P equal to 0.3. Sorry about that. And Y is equal to 3. So when we are examining 10 cycles, we have to go back and think of what we may see in terms of this table. Here n is equal to 4, but when we are examining 10 cycles, n is equal to 10, there will be how many rows of this table?
1000.
2 to the power n, which is 1024. So there'll be the table is going to be huge. And then the question that we are asked is, what is the possibility that we'll get 3 out of 10 failing? So then we have to zoom in on only those rows of this table in which there are 3 ones and 7 zeros. Or alternatively, if I add the values in those rows, I should get y equal to 3. How many such rows there are?
NC3.
NC3.
There are going to be n choose 3 such rows. And what is going to be the probability of each of those rows?
0.3 and 0.7.
0.3 and
0.3 to the
0.7.
power 3.
0.3 raised to 3, 0.7
0.3 to the power 3 and
0.7 to the 7.
to the power 7. Why is that? Because there are going to be always 3 ones and 7 zeros in each of these 10 to the power 3 rows. And therefore, probability of each row is going to be this much. So that is the calculation that I did over here. So this is the probability of each of those rows of that table. And there are going to be 120 such rows out of 1024. So the total probability of observing 3 cycles failing is going to be around 27%. It's way below 100%. Although we are told that P is equal to 0.3, if we look at only 10 cycles, there is only going to be 27% chance that we will see 3 failing. What are the chances that 2 will fail, or 5, or 10, or 0 will fail? That is what the binomial PDF tells us. It's like, again, a single, one complete answer, because it's probability mass function. It gives you all the probabilities. So that is what I have plotted over here. So you will see that this is the binomial PMF. If I ask what are the chances that I will see 3 out of 10 failing, then the binomial PMF will give you the same answer as what was there on the previous slide, which is around 0.27. But it also tells you that you, with a pretty good chance, maybe around 4% chance, you will see none of the cycles failing. and maybe you might see 6 cycles failing also with around 5% chance. The chances that you will see all 10 of them failing are pretty low. That's because P is equal to 0.3. So it's going to be pretty darn difficult for you to see all of them failing, but still that probability is close to 0, but it's not exactly 0. Okay. So as we have already discussed earlier, this is happening because n equal to 10 is not large enough. So now we'll see what happens as we increase n. But before that, I'll take a very okay. Sorry for the interrupt. I'm back again, and let us look at the shape that the binomial PMF takes as we increase n. Now, this is something that you can do yourself very easily, especially that you have done this binomial PMF evaluation in MATLAB in one of the earlier labs. It's just a matter of using MATLAB's binomial function, the binomial PMF function, and then plotting the values. So you can do this yourself also. Okay, so remember, this horizontal axis is going to show capital Y, which is the number of times that I see the bicycles failing when I do n number of experiments. And the value of n is the last value of this axis. So earlier we had n equal to 10. The only thing that I did now was to change n to 100. And so now you see that the values are actually concentrating around 30. You still see a pretty big deviation around 30, maybe somewhere between 18 to 42 or something. But other values, maybe 0 to 10, their probabilities become very, very tiny. And similarly, all the values above 50, their probability also became so tiny that we can almost think of them as pretty impossible. Not totally impossible, but they are very unlikely to occur. If I make n equal to 1,000, then I see even a greater concentration around p times n, which is 300 now. And the values that are departing from p times n become increasingly less likely. And if I make n equal to 1,000, then it's almost a spike at 3,000. Right? So this value where the probability mass function spikes up is always p times n. I think that is the answer that one of you gave. I don't know, maybe Vandan or someone else. So we see that for smaller values of n, where n is 10, it's almost impossible. I mean, it's very difficult to observe any spike happening at 3. You don't see the probability mass getting concentrated at p times n when n is small. But as we increase n, the probability mass does actually end up getting concentrated at p times n, meaning that all the other values of y become very, very less likely. Almost all the time we see y equal to 3,000. Right? So this is the observation that I said we already made. But we are making the same observation here in a little more mathematically rigorous manner. Right? So this is how I will write it. Okay, now there is again a little bit of sloppiness on my part. That Bernoulli variable here, unfortunately, it has become Q instead of P. So please pardon my mistake here. The notation is not as important as the idea. And so I hope that you have accepted this idea that as n becomes sufficiently large, there will be n times q cycles which will fail. And there will be n times 1 minus q cycles which will not fail. Or n times q ones and n times 1 minus q zeros. But this is going to happen only when n becomes sufficiently large. And the reason is what we already said, that if this was not the case, then we could not possibly call this a Bernoulli Q random variable. Because Q is actually defined based on the relative frequency definition as the limit value of this ratio. Okay, so this part is clear, I believe, to all now. Yes, no? Okay, thank you, Catherine.
Yes, sir.
Okay, good. So now this is clear. I'm going to start on looking at the same thing in a little different manner. And let us see how many of you can answer some one or two questions that are asked. Okay. So we have mentioned this earlier in yesterday's lecture that we actually don't need to go to variable length coding, because variable length coding has all this headache about ambiguity-free decoding, unique decodability aspect of it. If you don't ensure prefix-free mapping, then the decodability may either entirely fail or it may at least become difficult. And so variable length coding comes with its own baggage. It would be nice if we could do just the fixed length coding. But we said that fixed length coding is actually not optimal when the probability mass function is not uniform. But on the other hand, if the PMF is indeed uniform, then actually fixed length coding is the best thing you can do. If the DMS has 4 symbols and all of them occur with the same probability, then this is the best coding scheme. This is, you can't get any more data compression than what you have with this coding that I mentioned. Similarly, if there are 8 symbols and they all again are uniformly distributed, then this is the best scheme that you can have. Give 3 bits to each of the 8 symbols. Now, remember, one of the main observations that Shannon made was that when we look at an informative source, it is better if we look at not the individual output of the source, but we look at long sequences. So we essentially that n become larger and larger. So if I have a Bernoulli source and if I am looking at just one symbol, then unless q is equal to 0.5, I can't use fixed length code because q and 1 minus q are not going to be the same. But Shannon said that, well, we don't really need to stick to one symbol. Let's generate a long sequence of length n, and let's assume that we have a very fancy computer which can actually store such long sequences. And then suppose if we can have such long sequences represented in our computer, then what can we say about a sequence that we will observe out of this Bernoulli Q source? This is the question I have. Anybody has the answer?
One will occur q n times.
Yes. So Hemang is telling me the answer that I wanted to hear, which is actually the same answer that we went over just now. What we can say is that the sequence that we are going to observe will have n times q ones and n times 1 minus q zeros. Because this is what we have already concluded. So now, what about their probabilities? Do you think this sequence that we will observe, maybe one time we do this experiment, one time we draw out an n long sequence and we mathematically evaluate its probability. Then second time we again draw out a sequence and evaluate its probability. Do you think all these probabilities are going to be different or they're going to be the same?
If we take n very large, then a difference would be there, but very much small difference, like very small.
So let us assume that we have made n to be sufficiently large. And so we are seeing only those sequences which have n times q ones and n times 1 minus q zeros. Now, some of you said that therefore the probability is going to be the same of all any such sequence that we will observe. What is going to be that probability? Who can tell me that?
Probability of p raised to power n and 1 minus p raised to power n minus that y. Number of times nq is happening.
So remember, we are calling Bernoulli variable to have probability of q of being 1.
So it would be q and 1 minus q.
So it will be what?
Sir, it would be q raised to power the number of time ones occur and 1 minus q times the zeros occur.
So how many times ones are occurring? How many times zeros are occurring?
N times q times
nq and 1 n times 1 minus q.
So then what is the answer?
q raised to n qn1 minus q raised to n 1 minus.
Exactly. So Harsh gave the right answer. So I will see a particular sequence, maybe I'll call it sequence I, and it is guaranteed that I will see exactly n times q ones and I'll see n times 1 minus q zeros. Why is it guaranteed? Well, that is the whole argument that we went over. And then it doesn't matter when I perform this experiment or what particular sequence I see. If I am looking at the probability of that sequence, it is going to be always this. That is what Harsh has formulated just now. And you will see that this is very much like the formula of the binomial PMF. Except I didn't put that NCY term here. Why didn't I put that NCY term?
Sir, we are looking for one case.
Achyut mentioned it correctly that we are right now looking at the probability of only one such sequence. So I don't want to put that term here as of now. But now I'm going to play a mathematical trick. Okay, this is what actually Shannon did in his 1948 paper. So let us see what he came up with. So this is that probability that Harsh mentioned just now. Now what I'm going to do is I'm going to write it as 2 to the power log 2 and then put the same probability in the bracket of log 2. And so 2 to the power log 2 cancels out and I get the same thing. So the second line is just a clever way of writing the first line. And then the third line is just a simplification. In the logarithmic function, anything which is in the exponent comes out as multiplier. And then suddenly now, you see our entropy function sitting nicely here. This probably you didn't expect. So what are we saying now? We are saying that if I look at this Bernoulli source with some arbitrary value of Q, unless Q is equal to 0.5, I can't use fixed length coding. If I'm looking at only one symbol at a time coming out of this Bernoulli source. If I look at 10 symbols coming out of the source, then still I can't do fixed length coding because with 10 symbols, I'm going to get the type of binomial PMF that we had looked at. I can't use fixed length coding. But if I'm willing to make n sufficiently large, then I can say definitively that the corresponding source became a uniformly distributed source. All of its outputs have the same probability P of I, which is our definition of uniform distribution. And their probability is going to be same, and it can be written as 2 to the power negative n times the entropy of Q. So now this is the last question that I will ask you for today. What is the total number? So this is the question. This is the probability of each of those sequences. But what is the total number of such sequences?
Raised to n.
NCNQ.
And
N sequences.
Very good. Somebody said NCNQ. Who said that?
Me.
Kandak?
Yes, sir.
Very good answer. I like that. So that is the right answer. But then there is another answer which I am looking at. Who can tell me that answer?
1
NCY.
over pi.
NC N minus NQ.
Who said 1 over pi?
The Tarang.
Tarang. It's a great answer. Why do you think it is 1 over pi?
Sir, because the probability is the same for all the sources and they should all add to 1. Therefore, the number of sources can be written as 1 over pi.
I didn't like that explanation completely. Anybody else can tell me why it has to be 1 over pi? The answer to this question, one answer is that
Sir,
it
can I
is
explain?
N
Sir, can I
and Q.
explain again? Sir, because as the probability of, sir, suppose we assume that there are n sequences and the probability of each of them is same.
No. There are not n sequences. Capital N is not number of sequences.
This, I am assuming, suppose, means this is just a variable, and if we add pi n number of times, then we should be getting 1.
Why?
Because the summation of all the probabilities is 1.
Okay, who can expand upon this answer?
Sir, all events should be equally likely for fixed length coding.
Yeah, I mean that we already have said here, that all the sequences have the same probability, means that they are equally likely. That part is already here. The question is, what is the total number of such sequences? And Tarang said that it should be 1 over pi, which is actually the right answer. And the explanation that Tarang gave is also almost right, but not, there's some part missing. Okay, so in the interest of time, I will move forward. So we are asking what is the total number of such sequences, and let's call it capital K. So as Tarang mentioned, K times pi better be equal to 1. Why is that? Because first of all, these binary sequences are mutually exclusive. One binary sequence is not some other binary sequence. They are all different. And so we can then use this axiom number 3 of the Kolmogorow's probability definition, axiomatic definition, to say that the union of these atomic events is going to be a universal set whose probability is 1. Why is that? Because this is the part which was missing in your explanation earlier, that the DMS generates only these sequences as n becomes large. That is what we saw in those binomial PMF plots. All the other sequences, their probability became 0. Only the sequences for which y was equal to q times n, only those sequences remained. And so therefore, the universal set is comprised only of such sequences. Only such sequences can occur. No other sequence can occur. Because if some other sequence were to occur, then it means that the DMS doesn't have probability of 1 equal to Q. It just messes up everything. And so this universal set, which is what we are going to, from now on, we are going to call it the typical set. The typical set. Why typical? Because it is typical to see only members of this set. It is atypical to see any member outside of this set. And so we will, because we are going to see only the typical set, the probability of that typical set is equal to 1. And the probability of typical set is equal to also K times Pi. And therefore, K times Pi is equal to 1. So yes, one answer, what is the value of K is N choose NQ. But the other answer that is that K is equal to 1 over Pi. But Pi we have already formulated earlier. And therefore, we can write K is equal to N times HB of Q. And so now we can just go back. If I have K is equal to 4, if all of them are equally likely, then I need 2 bits. If K is equal to 8, 2 to the power 3. If all of them are equally likely, then I need 3 bits. So if K is equal to 2 to the power N times HBQ, how many bits do I need? I need only N times HBQ bits for that representation, and I can just use fixed length coding now. And I know that that is optimal. And that is the proof of the fundamental theorem of source coding, that I cannot have R less than HB of Q. This cannot happen. So we had mentioned this source coding theorem yesterday, and we had briefly mentioned in passing how to prove this theorem. This is the proof of that theorem. What does it really mean? What we are saying is that, and this is kind of a visual explanation, that suppose our DMS has total of 128 symbols and they are all equally likely. So their probability is 1 over 28, which is roughly 8 times 10 to the power minus 3. And I do fixed length coding, which is going to be 7 bits per symbol. And that is going to be same as entropy of the source, which is 7 bits. But now, if I consider some other source, which also has 128 symbols, but out of those 128, only 16 symbols have non-zero probability, and this probability is roughly 1 over 16.06. All the other 112 symbols have almost zero probability. So all of this has probability which is pretty close to zero, or it's nearly zero, meaning that they almost never occur. then this is sort of like our typical set. And this is all of those other atypical sets. And so clearly now, I can just ignore these 112 symbols because they are never going to occur. And so I can just use a fixed length coding with 4 bits. Although I have 128 symbols, meaning that although I have total of 2 to the power n sequences, the actual sequences that occur is only 2 to the power n times the entropy function. And so if I still use n bits to represent them, I am being wasteful of the bits. I can compress the data. I can reduce the number of bits from n to n times hb of q. Same way that I am able to reduce the number of bits from 7 to 4. But I cannot compress it any smaller than n times hb of q. The same way I cannot use any smaller than 4 bits here. If I use less than 4 bits, then I won't be able to capture all of the 16 symbols. And so that is why R cannot be less than hb of q. On a per symbol basis, I have to allocate hb of q bits. Okay, so that is it. Let me conclude that the importance of source coding in digital communication cannot be overemphasized. Not only in digital communication, in today's world, I would say, in today's technological world, unless you ignore what is happening outside, unless you ignore that Facebook and Instagram and many other such platforms are becoming very popular. There are a lot of videos which are getting uploaded to YouTube. Unless you ignore all of that, you have to accept that data compression is very important. If you can compress even data by a little bit, then you end up saving a lot of storage requirement. And you know, all these companies have big storage farms where it's nothing but just servers. And it takes a lot of energy and takes a lot of expense to maintain those servers. And so if you can reduce that requirement, then you actually help out a lot. So what we have done is, in our last few lectures, we have actually covered the basic mathematical framework and as well as not only the theorems, but some algorithms of source coding. And I think in an introductory course, this is good enough. In fact, it is great that if you have understood what we have covered, then you should consider yourself as having a lot of strong foundation now. Then you can build upon that foundation. Because a lot of the time source coding is combined with the quantization of the analog source, maybe the human speech, maybe the video, etc. And that is where still a lot of the questions are remaining, a lot of research problems are open. And that is where the machine learning techniques come into play. Because really an efficient source encoder combined with the quantizer is an intelligent machine. And there are already very smart algorithms that are used in all these such products that you know very well, Apple, Siri, Amazon, Alexa, etc. Because they do the quantization of the speech, but then they go above and beyond that. They understand what that speech is all about. And in order to do so, they use some advanced algorithms, linear prediction, regression, dynamic programming, and hidden Markov model. And they use AI techniques such as artificial neural networks. In addition, a lot of these algorithms also make use of Fourier transformation that we are going to study next, as well as DCT, as well as wavelet. These are all very important topics. If you want to advance in machine learning, then you have to be on top of all these techniques. And if you become expert in these topics, then who knows, maybe one day you will launch a startup which is able to do some amazing data compression of some audio or some video, and you will become super rich. That is all for today.